All right, welcome back. Today is October the 16th, and we're going to finish up practice homework 7. And so, I have to switch here. Yeah, for you guys, the last thing that we had to cover here was the reaction mechanism on the last page. And so this is hydration. So let me lower my computer here. All right, so how do I know it's hydration? Well, I see.
I can't see your screen.
Oh, thank you.
You're welcome.
Thought I had hit this. Now you can see it, right?
Yes.
Okay, thank you. All right, so like I was saying, this is hydration. And I noticed that I have water and I have acid, and that's good enough for me to know that that's hydration. And then this magnesium sulfate, the book calls it oxymercuration, but I don't think so. I think you can do this reaction without it. It doesn't make a difference to like lock the mercury here. Besides, this is this is mercury too, but the actual oxymercuration, we form mercury plus. I don't see how you can form mercury plus from here. Never mind. So let's just continue. All right. So basically, you will see why I say that the mercury sulfate here does absolutely nothing, because I don't see it involved in the mechanism. Check it out. So we start with this is 1, 2, 3, 4 carbons. So this is but-1-ine, and I'm gonna use sulfuric acid. I can use sulfuric acid here, or I can say that I have H3O plus, right? We mentioned that before. This is your choice. All right, and so the triple bond is the nucleophile. It goes after the hydrogen, and the bond in the hydrogen is transferred to the oxygen. All right, because sulfuric acid looks like this. All right, and so you are deprotonating here, then this electrons are transferred to the oxygen. That's why when I do it like this, I make sure that I'm transferring the electrons to the oxygen. All right, and so what does that give me? That gives me an alkene. Now I have 2 hydrogens here instead of 1, and I have a plus sign here. You see that? So your conjugate bases will be HSO4 minus, or water if you use H3O plus. So for the H3O plus, you would have done that and then that in green. All right. And then now you'll hear then water comes into play, and then it's going to attack the plus sign. Notice that that plus sign doesn't migrate. It's not a free carbocation because it's on a double bond, so it's trapped there. So the alcohol attacks, the water attacks, and You don't need to draw these H's that I am doing here. Good morning, Kaylee. I can see you. And so this water will be plus. All right. So I like to put the plus with a circle there, so that looks kind of cool. Cool to me. I don't know if it's cool to you, but it's cool to me. All right. So let me see one thing here. Yeah, I think I'm gonna continue on the right side. Then what do we need to do here? We need to get rid of one proton, right? So how would you do it? Well, use water. Use water. You can use water. Your choices are water or HSO4 minus. And so if either one of them will regenerate the acid, H3O plus. So I'm gonna do it like this. I like to do it like this. And then or join this one here. Whichever one of this that you choose is fine. And so when that does that, those two electrons here are gonna be transferred to the oxygen. So far we have 3 steps. And so we'll get this. And I have that OH plus H3O plus or H2SO4. So you regenerated back your acid. And you can go back to the start and start catalyzing another alkyne. All right, so we're here. And so then we're gonna, so this is the enol form. So this is the enol. So we're gonna go from the enol to the keto. And that is done in 3 steps from here. So we're gonna go from here to like, I'm gonna write it down around here, but I don't think I'm gonna get there. But in that little space, but I'll try. And so from here, this is all gonna be called tautomerization, because now we're gonna formally tautomerize this enol, and we use acid. We use acid again, H2SO4, double bond. It's gonna grab. It's gonna go and grab that H. Let me think about this step for a second. Yeah, let's do it like this. I'm gonna grab a proton, and that's gonna be a 3rd proton on the terminal carbon.
Why wouldn't it grab the H on the OH?
Why wouldn't it go like this? Because it needs.
I mean, the acid, like from the previous step, you know how? Oh, I guess it's because it doesn't have a negative charge.
Yeah, it doesn't have a negative charge, and also the acid catalyzes the reaction, so you need to put it somewhere.
Okay.
And so now you have 3 H's, the 2 that you started with plus the 1 from the acid, and then you have an OH, and then your plus is right here, right? That is perfect, because this oxygen is electron rich, and so it's going to make a carbonyl. And so what else you have here? You also had, so remember that I forgot to do this. Always push those electrons out. I was distracted. Or you can also use H3O plus here. Again, your choice. And so when we do that, when we do this step, we also have now HSO4 minus or water. All right. Then we're almost there. We have made something that looks like a carbonyl group. So this is that, and then check this out. One of these two guys, most likely this, or water, will grab that H, and those electrons from this bond will transfer to the oxygen, and you will form your ketone. And this is the final product. And all of this that we did here, from the enol to the ketone, is tautomerization.
How did you know to draw the end, like starting going down? The keto structure, how did you know to start? Like, why is it drawn differently, if that makes sense?
From where? From the enol to the ketone?
From the one that we just got off of.
Oh, from here to
like
here?
You see how it's down and then over and then double bond?
That doesn't matter. Mia, there's free rotation here on this carbon. So this could be down or it could be up. That's what you're talking about? It is, yes. Yeah, the same thing. Okay. I could have done this and that's the same thing. You just have free rotation.
Oh, okay.
You see it? Uh-huh. But
yes, I see it.
Yeah, once it's like the final structure, it's almost kind of cool to like do it like in a zigzag. Because most books will show you that here we are forced to draw it like that because we have a linear structure. But once the molecule starts to rearrange, you go from linear to sp2, trigonal planar, to trigonal planar and tetrahedral structures, which is that. Yeah. All right.
I have a question real quick.
Yeah, go ahead. Who's this?
This is Hannah.
Hannah. Oh, hi, Hannah.
Hey. Is a keto the same as a ketone?
That's a good question. It's like a generic form. So a keto for tautomization could be a ketone, or it could be an aldehyde. It's kind of weird why they call it keto. Honestly, in this case, it worked out to be a ketone. This is butan 2-on. It's butanone. We're gonna learn next year that ketones are called with the ending on, not one, but on. And so in this case, it worked out to be a keto, but sometimes the keto form is an aldehyde, so it doesn't make any sense. I think a better terminology would have been a carbo. They should have called it a carbo.
Yeah, because of the carbonyl.
Because of the carbonyl, yeah, and then it's for both carbonyls, but they didn't ask for my opinion, so so they went with keto. So that's what happens. Yeah.
Thank you.
You're welcome. But I agree with you. This is not a universal term that involves both the aldehyde and the ketone. Yeah. All right. Any other question about this? notice that at this level now you're supposed to push all those electrons like I did here. And you can choose what base you want to use or which acid you want to start with right here. It doesn't really matter because we established that an acid is H3O plus or any other acid in water. Yeah, and so this is chapter 7. It's now going to the record books for 2020. All right, so I'm gonna stop here unless there's a question from this. Let's take a moment to like finalize this practice homework. Anybody has a quick question that needs reviewing?
Is the quiz going to be over just chapter 7?
Oh yeah, absolutely. We're gonna split chapter 7 quiz, and then we're gonna do a quiz on chapter 8, and most likely we'll have a quiz on chapter 9. And if we have time, we'll do another quiz. So maybe we can drop 2 instead of 1, but I'm planning on dropping at least 1 more. So in the first half of the semester, we were able to fit in 3 quizzes. My quizzes usually last 10 to 15 minutes, but because of COVID, I had to give you 25 minutes because I had to involve the DRC students that require more time. So I involve everybody and give 25 minutes, but that kills half of the class period. So, but that's what it is. Yeah. So I'll try to put mechanisms questions on the homework so that you practice, because the one skill that I'm worried that you're missing out because of the electronic thingy that we have right now is this: your ability to push electrons in a smooth, flowy way. And this is a huge component of OCHEM, and I am all for mechanisms. The 2 semesters notes is geared towards mechanisms. So this is killing me in a way, because I really want you to get good at this stuff. It's either this or memorization. So what would you prefer? I prefer mechanisms, because I don't have to memorize anything. But the way we have set up these online courses, it's usually the online courses are only good for mostly good for courses with definitions. And we have some, but we're not really built for that. All right. Any other questions about chapter 7? If not, I'm going to start a new section. Ta-da! Practice homework 8. Yeah. I hear a roar of people saying, yes, yes, yes. We got this. All right. So, practice homework 8. It's not bad. It's actually pretty easy. The concepts are straightforward. Some of them you have to analyze. Until you get to Diels-Alders, I'm going to teach you how to predict with precision the final product of a Diels-Alders. Why is that important? Well, let me tell you an anecdote. When I was at Wake Forest, there was a competition among faculty, and we were designing a synthesis, total synthesis. We got like a molecule, and we had to present it. I mean, the finalists will present it, and so it was my turn to present mine. I had a total synthesis that had the the fault of my synthesis was that I started with a step that will give me 50% yield because it will form two products. And I said, well, I'll make the 50% yield. I cut my losses, I purify it, and then I carry on with the isomer that I need. And so there was this dude from another school that he also was a finalist, so he had the right to, like, bombard me with questions. And then he was saying, like, okay, your mechanism had this flow. Every time he wanted to talk about my mechanism, he went back to that first step. Okay, I handle it. And at least I was honest, from the beginning. Then he was his turn, and he based all of his effort on a Diels alders that was 500 degrees, and he actually didn't get the right stereochemistry. I was able to pick it apart thanks to these guys, thanks to this thing that I'm going to teach you. And then ask him two questions. One of the things about the guidelines was this synthesis needs to be done in the laboratory at normal temperature and conditions. Normal laboratory conditions and temperature. And so when I saw his Diels alders reaction, I asked him a very naive question. I said, so where are you going to run that reaction? In the roof? Everybody was laughing, and I didn't mean it that way. But it's because in Florida, when I went to do my PhD, we did all the Diels alders reactions in the roof, on the roof. And so on the roof, we had some little cubicles with steel walls, and the doors, you can open the doors, they slide it, you can slide them, and they were made out of steel. And the next day, sometimes you just see like shattered glass all over the place because those reactions were explosive. And then I said to him, and then I have another question. I think your final product will have the wrong stereochemistry. And I won the competition. It was him versus me, the final two, and I beat him because I knew the Diels alders reactions because I teach it to my students. And so that's why I want you to learn it. You never know. You never know if these reactions might give you a job or might make you win a competition. You never know. But that's my 2-cent stories for the morning. All right, so let's begin this chapter. Chapter 8. All right. So practice homework 8. It's about aromaticity. And I want to open quickly some of these historical features about aromaticity. I don't know, you have probably heard the last name Faraday. It's very commonly in science. This dude was British, and he isolated in 1825, and identified an oil that was kind of different. And it was from residues of the gas lamps in London. Talked about, environmental scientists right there. My boy Faraday, good job, man. And so, but he didn't know what it was. He just knew there was a different oil. And then later, in 1865, this dude, Friedrich August Kekulé, in 1865, he said, "Oh, I'm gonna propose the structure of benzene," and he proposed it with a chromy dream. If you've seen my videos, he talks about where he was dreaming about snakes, and they were dancing in his head, and it's all baloney. And then one snake beat the tail of the other one beat the tail of the other one, the third one bit detailed of the first one. So he made the benzene ring, and he proposed the structure of the benzene ring based on that dream. Yeah, right. I think he just planned it. So, and then he became notorious for that dream, and we're still talking about that fake dream nowadays. But it's just funny to me, and that's why I still talk about it, because it amuses me. And so until recently, like in the 1900s, then we came up with better methods of identifying the benzene ring, because we compare benzene to cyclohexene by doing the bromine test. Bromine is a really cool test. You can check it out on YouTube if you want to. Just type bromine test on alkenes, and you'll see that this is an, they say red brown, but this is most likely like an orange. This is an orange liquid that you add dropwise to the alkene, and the alkene will make that orange color disappear. So it just absorbs it, bloop, 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 one drop at a time. And what it's doing is making sigma bonds of carbon and bromines, makes those two. And later we found that it was enantiomers, because it does the bromonium ion and all that stuff that you know. But the benzene wouldn't do it. There's no reaction on that. And so then a new legend called benzene was born. Then we realized that this material, this chemical, will not undergo addition. What it will undergo will be substitution. And we're going to learn about electrophilic aromatic substitutions, EAS reactions, next semester, where you replace an H and put the halogen, in this case the bromine. And so that's how this reaction will actually work. All right. And then they did a whole bunch of different comparisons again. And we can see that because benzene actually requires really harsh conditions to be fully reduced from three double bonds to 6 sigma bonds total. Then compare that to cyclohexene, we can see that there is the heat of hydrogenation for 3 double bonds will be 3 times 28.6, that's 85.8, and the total heat of hydrogenation for 3 double bonds in benzene takes 49.8. We'll believe that there is the difference of 36 kcals per mole means that the benzene has what is called resonance stabilization, and that makes it more stable, therefore less reactive. You see that? Based on these numbers. Okay, and then we're going to, I hope you've seen my videos, but we're going to do some molecular models, and we use the shape of the rings. And so if we have six carbons, so that's 6 different molecular orbitals. We're gonna put 6 lines. And if you have 4, like this cyclobutan 1,3-dione, we put 4 lines. But we always start with a low line. This line is always the most lowest in energy. So we have to set it up like that. And we look for symmetry. And I teach you several examples where we look for symmetry. Like, notice that here is my benzene ring. It's like that. All right, based on the 6 molecular orbitals, and here's my cyclobut 1,3-diene. It's a 4-member ring, and it looks flat. Some of them will fall into the aromatic category. Some of them will fall into the anti-aromatic. So here are the conditions for that. So we see that aromatics, here are the 3 conditions. It needs to be cyclic, it needs to be confirmed planar, and it needs to be fully conjugated with a field highest occupied molecular orbital, also known as HOMO. All right. Then the anti-aromatics will be cyclic. They could be planar, they could be fully conjugated, but you will see that a lot of the times they only have a half field highest occupied molecular orbital. All right. Then in between the two, there is the non-aromatics, and usually if any of those conditions is violated, either cyclic, planar, or fully conjugated, then it's considered non-aromatic. Most likely non-aromatic, you will see them, you will spot them because you might see a carbon that is sp3, or if it's a ring, it's usually non-planar. And I think those are the 2 most common, but they also if it's not fully conjugated, this not fully conjugated means it has an sp3 carbon somewhere, and usually they're not cyclic. Also, if it's not cyclic, well, you know that it's non-aromatic. And so I give you examples of them, how, for example, here we thought it was anti-aromatic until we needed a little extra information, so we came back to this slide, and then we confirmed that it was non-aromatic right here on the next slide, because up to this slide we see cyclooctatetraene. It has 4 pairs of pi electrons. It has 8 pi electrons total, and when we do this, we notice that it has a tubular shape, and so it's non-planar. Therefore, it breaks one of the criteria for anti-aromatic in this case, because we already said that it was anti-aromatic because it had half-filled HOMO, and it turns out to be non-aromatic at all. All right, so now I'll give you more examples. Notice that here's my 3-member ring. Looks like a triangle, right? This one looks like 5. That will look like that. That is the shape of that. The cyclopentadiene. This one is more difficult, but here we have 10 carbons, so that's 5 pairs of pi electrons. And notice that we always only fill the orbitals that doesn't have the asterisk, meaning if you have an electron on an anti-bonding, then the molecule will not exist. All right. Then we'll learn about Huckel's rule. And Huckel's rule states that you have to fit the number of pair of pi electrons in this n. Here, this is a formula. It's 4 times n plus 2. Please watch my video on this. You need to know this stuff. And then I'll give you examples here. When n is equals to 0, then 4 times 0 is 0 plus 2 is 2. So there's 1 pair. If you have odd numbers of pairs of electrons, then it's aromatic. If you have them as even, then they are not, they are anti-aromatic. And if any of the three conditions is violated, then the molecule is non-aromatic. Give you more examples until we get to some sort of problems like, let's see, I also have some problems like this one here. So judging reaction reactivity, does this compound act as an acid or base? And then the answer is it acts as an acid because right now, the way it is right now is non-aromatic. But if you protonate, if you take this H, it leaves one lone pair, and that lone pair gives him 3 pairs of pi electrons, which makes it aromatic. So it wants to attain that. So if the starting material could turn aromatic, it will do it. That will be a driving force for the reaction. And then we haven't gotten to SN1 or SN2 yet, but I always like to give examples right before we introduce that topic and we like develop it in full. But then he said, judging this reaction reactivity, does the reaction follow SN1 or SN2 route? And so it cannot undergo SN1 because the SN1 it'll make this compound where it has 4 pi electrons and 2 pairs. 2 pairs is anti-aromatic, so it will prefer the SN2 because with the SN2 it is non-aromatic. So let me write that down. But this one is non-aromatic because it has an sp3 carbon. But non-aromatic is higher. I'm sorry, it's lower. See, non-aromatic is lower in the energy diagram than the anti-aromatic. So aromatic is the most stable. The next most stable is non-aromatic, and the least stable is anti-aromatic. And so it prefers to, choosing between this and that, it prefers non-aromatic because it's lower in energy. So those concepts now, you have to put them together. Yeah. You put them together here in this type of questions. And maybe this is as difficult as it's gonna get up to this point before we do the Diels-Alders. In the Diels-Alders, we'll learn that this is a 4+2. This is the first type of rearrangement reactions that I talked about. This is the 4th of the 5 types of reactions in organic chemistry. We're going to learn this amazing reaction name in great detail. So after we do the Diels-Alders, I show you the models, how to do it. I have a few models here that are really, really good. You'll be able to identify the Diels-Alders reaction. Then we get to polymers. We need to teach polymers at this level. So this is the only chance, I think, that the book gives us. And so I introduce the topic and I show you how to make polymers, and we'll try to identify the monomer or the pattern. Here's the monomers. I explained this in great detail in the videos. So if you still don't understand this, you need to ask me, and I will be more than happy to explain that. But yeah, so on the polymers, you will have always a nucleophile that attacks. And once this other bond breaks, that becomes the nucleophile of the next one, and the nucleophile for the next one, and it keeps going on and on and on and on. And we make these long polymeric materials that are used for everything, like for clothing, ropes, medical devices, you name it, anything. And this is all organic chemistry. So this is polymers. The polymers is an organic chemistry field on its own. You can get a PhD on just polymers. And I heard they're really hard to purify sometimes. So I was never interested in that, but I know about them. And so, yeah. Then that's the end of this chapter. Rather long chapter, but fun. Let's do the homework, the practice homework. All right, we have 6 minutes. We're gonna do the first one at least to get you acclimated. Question I have here: explain which of these compounds is a stronger acid, and why. So, in order for you to explain which is a stronger acid, you need to draw the conjugate base of those rings. So let's start with the left one. Check this out. The left compound, if you deprotonate one of these H's, let's say I deprotonate this H, and I leave the 2 electrons that are here on this bond, I'm gonna leave it like that. But there is an H there too, so there's an H that is right there. All right. Because these are linear structures, I'm just gonna delete that H. Oops, I deleted too much. This pen eraser is very aggressive. I'm just gonna leave it like this, so it's neat and cleaner. But no, there's an H there. All right. So how many pair of electrons can you read here? So there's how many pairs of pi electrons you read? I hope you've been watching the videos, because when the practice homework come up, it's expected that you know this thing. At least watch the first 2 videos or something. How many pairs do you read?
Is it 2 pairs?
It's 3. So we have 2, 4,
I was
6.
just at the one. Yeah.
Uh-huh.
I thought you were talking about the double bonds.
Oh, no. Yeah, I mean, notice that something, Hannah. This lone pair are in a p orbital, and this p orbital is 1 carbon away from a double bond, so they are conjugated, and so they count. So you have 3 pairs of pi electrons. In total, you have 6 pi electrons here. All right. So the 3 pairs goes along with what my man Huckel said. Where is Huckel? Let's see. Give me a second. Right here. Huckel's rule says, if you have an odd number pair of electrons, then the molecule is aromatic. How cool is that? So we found that out. Let's see the other one. This guy has 2 electrons here, I mean 2 hydrogens. If we deprotonate 1, what do we get? So we will have, so it's a 7-member ring. So to make a 7-member ring, I put 3 dots, like a little house, and then I make a little boat here with 4, and I connect those dots. All right. I don't like it. So I'm just gonna draw it. But that's how you do it. Now that's better. Now we'll do this, and now we have that. How many pair of pi electrons do you read? Pairs now. 4, right? 4 pairs of pi electrons. In total, you have 8 pi electrons. So this molecule, it's, according to Huckles, is anti-aromatic because we have 4 pairs. So this, in other words, this molecule will be aromatic, and this molecule right here will be anti-aromatic. All right, so this will form. So the left compound will form, and it's a stronger acid because its conjugate base is aromatic. Let me write that down. Because it says which of these compounds is a stronger acid. So the left compound is a stronger acid because its conjugate base is aromatic. Now you understand the term aromatic. Now I hope. Let's do the next one. Let's see if we can fit one more. So based on this, check this out. If you do the conjugate base of the molecule on the left, let me change pens. You have a double bond there, and which proton will you deprotonate? This one, right? There's a proton there and a proton there. If you were to deprotonate that proton and you put a lone pair there with a negative charge. Oh, by the way, this one has a negative charge. My bad, I forgot. Please take notes. Now this one will have 4 pi electrons, meaning it has 2 pairs of pi electrons. This molecule, according to Huckel, will be anti-aromatic right there. So this is anti-aromatic. The other one, this one, will simply be non-aromatic. Why is that? Because we have sp3 carbons here, and that makes it non-aromatic, and so the right compound, the compound on the right, will be the stronger acid. because its conjugate base is non-aromatic, and that is lower in energy. That's lower in energy than the anti-aromatic. All right, so think about it for this one here, and we'll do that on Monday. Have a wonderful day, guys.